All right, everyone back. Okay, let's resume the recording. All right, so now let's hop into simple regression. All right, so for our correlation is essentially telling us, okay, is there a relationship between these two variables? Are they moving together? Are they covariating together? And what is that, what is the strength, what is the direction of the relationship? But what correlation does not tell us is how to predict anything. So if we want to predict Y on the basis of X, for example, so what if I wanted to predict based on how many ads someone saw, how many cookies were they going to buy, for example, then rather than just seeing if a relationship exists, then we need regression. And so we're going to start with simple regression, and then next week we'll move into multiple regression. So for now, we're still just going to be dealing with 1Y, 1X. And so this is going to go back to your sort of high school math where you think about the equation to fit or to draw a line, right? So in high school, I think I always learned it. Y is mx plus b, right? If you wanted to plot a line, back to your high school like geometry or whatever class that was. So that's very simple, exact. It's going to be a very similar concept because we're basically going to try to find the best fitting line that is going to help us predict Y based on X superimposed on the data. So we're going to use that same formula wherein, except we're going to flip it around where we'll have B first and then our MX second, where B is our intercept and M is the slope. And so remember, your slope is rise over run, your intercept is where you're sort of starting, so where it crosses the y-axis. And so for regression, we're going to write the equation this way or this way. So you might see it written either of these two ways. You'll notice this is a y with a little caret above it. So this is called y hat. Whenever you see it written this way, that y hat is referring to the predicted value. So y, there are values of y, and then we're going to have the predicted values of y. So we'll call that y hat. Then we'll call this beta 0 or the slope, and then plus the beta 1 times x. And so eventually once we, beta 0 is the intercept. Sorry, getting my words mixed up. Beta 0 is the intercept, and then beta 1 is the slope. So that's the change associated with y with 1 unit increase in x. And so you might also see these written as lowercase. Typically, when they're uppercase, this refers to standardized beta values, and when they're lowercase, they're unstandardized. We'll talk about what standardized versus unstandardized means in just a little bit, but just so you know, we're going to be derived from the same formula. It's just whether or not they're all in standard deviation units, which is what the standardized beta values are. So beta 0 is going to be the intercept. So this is the value of y hat whenever x equals 0. So whenever x is 0, what is y equal to? That's your intercept. So it's basically your starting point. And then whenever you think about your slope or beta 1, this is that change in y hat associated with a 1 unit change in x. So as you move from, for example, down here, as you move from 4 adds to 5 adds, what is the change associated with y associated with that change from x? So here's a probably better example of this. So this is the same data here, where you can see here our intercept is where we cross the y-axis, our sort of starting point, your 1 unit change. So as you move from this value of x to the next value of x, so let's say from 4 adds to 5 adds, that distance, the change associated, this is the slope. So at that angle, so that's the rise over run. So you can just think about the tilt of the line there. And then your line represents the predicted values that you would predict based on that regression formula, and the distance between each actual data point and the line. This is called your error. You'll also see these called residuals. This is not that different than what we talked about with ANOVA. Remember, with the error term, your residuals, what's left over. So it's the difference between what we predicted and what we actually observed. So questions about this?
Yeah, I have a dumb question, sorry, but the 1 unit change in x, units aren't based on the individual data points. That doesn't have to be the case, because that looks like 2.5 or something.
No, so it's based on, if I had this axis still here, it's from going from 2 adds to 3 adds. So 1 unit change. So as
I'm on the last page. I'm sorry.
Yeah. So essentially, but if you were doing the same, it's not based on the data points themselves so much as the where the data is. So what category? So if they watched 1 ad versus 2 ads versus 3 ads, so going from 1 to 2, that's a 1 unit change. Or from 2
okay.
to 3, that's a 1 unit change. Yeah. So it's a 1 unit change across the x-axis. So into your different ad categories. So if we wanted to plot our essentially our actual data or our outcome, this is going to be captured by our typical regression formula or your typical line formula plus error. So your intercept plus your predictor variable times, so your intercept plus your slope times your predictor variable plus error, that gives you all the data, because the regression formula gives you the line, the plus E at the end gives you those distances, the error that you have. So, and this is your random error term. And we know that error always happens because we're never going to have a model that perfectly predicts our data, right? So if you ever, so right now we're in linear regression, and it's beyond the scope of this class, but eventually you can get into nonlinear situations where you actually can get a little bit of curvature in your lines, or you can start modeling interactions where you can actually model your data. We could model the data to fit every single data point here, but what would be the problem with that? Where we would have no error term. But what would you foresee the problem being with that if my goal is prediction? So if I want to model this data, and now I have a formula that I know, okay, this best estimates my data and it fits perfectly. When I feed new data in to predict those values, what would be an issue?
Your slope won't be linear. That will affect your slope.
Yeah, so that would be one problem. So it would no longer be linear. So it would be out of the linear regression world. So, but there are types of modeling that you can do where it's not linear, and we could fit things exactly. But if I wanted then to put in new data and predict new things, do you think it would be very accurate? So then if I went and recollected this study with different subjects and then said, well, I don't have to do regression. I already modeled this once with my old data and I fit it perfectly, and then I use that model on my new data, is it going to do very well? Probably not, because if I fit this perfectly, right, it's only going to explain this data and it's not going to explain new data. And so in the modeling world, there's always this balance between fit and overfitting. So especially after you get into more complex modeling and sort of out of, if you get into like multivariate stuff, there's this overfit issue where you can model your data too well to the extent that it no longer is useful for other data sets. And so we call this problem, it doesn't generalize. So you can't use it for anything else because you've overfit your data. So while we do want to minimize our error, you're never going to eliminate it. And that's always going to be true in linear regression. Anytime you're in linear regression, like someone mentioned, we're going to have a straight line because it's linear. So that's one of the assumptions of linear regression. But if you ever get into more advanced stats classes, I'm not sure what all classes you guys end up taking, and you start getting into multivariate stuff where you can start actually overfitting your data, and some of these assumptions are more relaxed, that becomes a problem because now you have to balance how well do you want your model to fit versus how well do you want it to perform whenever it has to predict new data, when it has to see new data. So even though error is not great, we want to minimize it. You're never going to eliminate error. So you're always going to have this error term here at the end. All right, so our goal is to find this regression line. So if we have data points, we want to find the line that best fits our data, right? So with simple regression, we're just going to solve for our intercept and our slope, whatever values that produce the best fitting linear function. So we will use the data that we already have to fit that line. So it's essentially just going to be some algebra. But from a conceptual perspective, we can say, okay, what does best fitting mean? So what does it mean that we find the best fitting line here, that we don't have, that we make sure that we go through the mean, or is it that we want to minimize the error across all data points, or just minimize the error at one data point? Do we want to try to go through as many data points as possible? There are a bunch of ways you can draw a straight line, right? So we have to sort of think, okay, what does best fitting mean here? So the traditional way that we're going to look at that is, okay, we're going to look at prediction errors. So the differences between y and y hat. And remember, y hat is your predicted values, y is your observed or your actual values. So this is very similar to looking at deviations from the mean, right? So, but now we're looking at actual minus predicted. And so we'll often refer to these as prediction errors or residuals. And so what we want to do is find the set of residuals or set of y minus y hat that minimizes these errors. So how can we figure out which line is going to give us the smallest amount of residuals? But you have to remember, we have a whole data set of y's. We don't just have one y, right? So we're not just looking at this data point and minimizing this error. We want to minimize overall across all of our data points. And so we have to use some kind of summary statistic to capture all of the errors at once, because we can't just be looking at 18 different errors at the same time. So we need some type of summary. And so what do we typically do in these situations that you've seen that all throughout this course when we're looking at deviations from some other metric and we want to summarize them? What do we always do? Or what's one solution? There are a couple things, but think about sums of squares. So we look at deviations from the mean, and then how do we summarize that? We sum them. So remember, we deviations from the mean, we square them and sum them, right? So that's essentially what we're going to do here. So we have we're going to take each of our deviations from predicted and observed and sum all of those errors. But again, just like with sums of squares, there's going to be a problem. So this is a different problem. So we can't just try to minimize the sum of these errors because there are a bunch of different lines that will go through the mean of X and the mean of Y. And if we sum those errors, it's always going to sum to 0. So I guess similar to the issue that we have with sums of squares, right? Because if we take all the differences from the means, calculate those sums, it's always going to be 0 unless we square it. So we're going to be facing this problem once again. So, oh no. So I have this code in R that we can actually go through. But essentially, if we could draw a whole bunch of different lines here. So I could draw a horizontal line. I could draw this blue line here. So we could draw all these different lines. Our task is really to find out how do we get the best fitting line and how do we minimize all of our residuals. But if we, and I'll show this in R in just a second, if we calculate all of the residuals from this data point to its line, this data point to this line, and we sum all of those, they will always equal 0 if that's all we're doing, it's just summing them. So that's not going to help us find the minimal amount of error because it's always going to be 0 for whatever line we draw that goes through the means. And clearly you can see some of these lines fit better than others, right? So this purple line is horrible. This is not fitting the data at all, but just summing the residuals will give you a sum of 0 because it's intersecting the mean. So what is our solution to this?
Can't you do absolute value somewhere?
We could do absolute values. Yeah, that may work, but what do we usually do when this is a problem with sums of squares? Oh, because also, yeah, so you can do absolute values because it's going to do essentially the same thing. But what is our sums of squares solution that we always do? But we square our residuals, right? So we take the deviations from the mean, square them, and then we sum them. Exact same concept here, because otherwise it's going to sum to 0. And so now our job is not to minimize the residuals, but really we're going to minimize the sum of the squared residuals here. And so this is often referred to as the, oops, what is happening? This is referred to as the method of least squares. And so you might often see this called, least squares or minimizing least squares. And so because we're trying to find the smallest squared residuals, essentially. So very, very similar to what we do with variance, except we're doing deviations from the mean there. And now we're talking about deviations from a regression line. It's the exact same concept. And so in order to minimize the sum of squared errors or SSE or sum of squared residuals or SSR, these are identical terms. It's just some people call it sum of squared errors, some people call it sum of squared residuals. We're going to solve for our intercept and slope using these formulas, and this will allow us to get the minimum number of squared residuals. And so remember our covariance that we calculated earlier, we're going to need that again. And then we're going to, because now we're actually using X to predict Y, we're only going to divide by the variance of X instead of including variability from Y. And then we'll include this in order to calculate our, finish the algebraic equation here. In R, we'll actually go through these steps, but in R, we've already done this before with the function LM. All it is your outcome tilde predictor. So we've done this with ANOVA tons of times because it's essentially doing the same thing as ANOVA, which we will get to after we go through some of this R code. So the first thing I want to do is hop into R. We'll go through some of this math, and then we'll get back to the conceptual stuff. So, all right, so if we come down here to my line 47-ish, so it might be lower on your guys' lines or your guys' scripts. All right, make this bigger. So what I'm going to do is plot. So I've already got some code in there that will plot our data. So this is our ads watched versus cookies bought or whatever thing that we're measuring here. So you can see we don't have much data here, but so this is from our, our correlation that we did. So we could draw a line through these, right? And if we wanted to draw the best fitting line, I can already tell you, spoiler alert, if we use LM, a bought, so how many ads they bought or how many cookies they bought versus their ads, and use this AB line, this is going to plot the regression line. So AB line is a function that goes with the plot function. So just like we're adding layers to a plot, AB line is doing that. And I'm just putting in the entire regression object, and it's going to pass that entire line. But you can also imagine that we could just plot, let's say we want to highlight our means for X and Y. So I'm just going to calculate down here. Actually, I'll do it up here. So I'll just calculate the mean for X and the mean for Y, just so we have it. So 5.4 and 11. So if I wanted to add those in, so I'm going to do 5.4 and 11. So I'm just adding in points of 5.4 and 11, and I'm going to color them green, just so we can see the mean. So these aren't actual data points necessarily that are in the data set. These are just the means that I'm trying to highlight. I'm going to make them a little bit bigger, so I could add those in. So now you see here, this is where our mean is. So you see how our regression line intersects our mean. So our mean is not a data point. And so that often happens, right? Your mean doesn't have to exist within your data set, but our regression line intersects that mean. So we could try other lines that also intersect our means. So let's try a line at 5.6 and 1. So giving it our X and Y coordinates, and I'm going to color this one red, for example. So I could try a line here. So, and this one also intersects our mean, right? So we could do a whole bunch of different lines here. And this is essentially the code that creates that graph that I have in the PowerPoint. So if you want to, if you're playing around and you want to go back and create it. Let's see. I'm going to change this to blue, and you can do whatever colors you want.
I am asking a really stupid question. This LM is from ANOVA, right? This was one of the ways you could.
Yes, so that's actually not a stupid question. It is from ANOVA, but it's actually called linear model. So LM is actually the default way to do regression, and we just used it for ANOVA because regression, ANOVA is a form of regression. Just from, think about regression as like sort of like the backdoor look inside of ANOVA. So ANOVA is when we lay out the table and sort of go through sums of squares and everything. Regression is doing the same thing, but in a different way. So it's doing it by calculating these lines, but it's still all trying to minimize these residuals. But yes, we did use it for ANOVA, but it is the default for doing regression. So if we do adding in these lines here, you can see here, oh, our blue one, I must not have done that blue one correctly. Can't remember what that one was supposed to be. They were all supposed to go through the mean. Oh, that's supposed to be a 2. So now you can see here, so all of these lines go through the mean, right? But some of them fit better than others. So obviously this purple line is doing a really bad job of fitting all these data points. This red one is also doing a decent job, but not as good as the black one, right? Because the black one is actually the regression line. So to illustrate why we can't just sum these residuals, let's actually calculate some of the sum of residuals of these lines. So we have the intercepts and slopes of all these lines that we just calculated. So let's just calculate our predicted values. So let's say we want our, so I'm going to run this. Our first ones are intercept of 5.6 and 1. So I'm running this first red line. So that red line would predict that our values go to, we're going to do slope times our x, right? So our x, this is our predictor. So the thing that we're predicting times our slope plus the intercept. So you should get something like this. So if we use the red line, these are the values we would predict. Remember, these are the values we actually have. So do you see the difference between these? It predicted 10, it was actually 5. It predicted 9.6, it was actually 4. So can you see how the red line is not doing a very good job? So I'm just going to call our values that the observed values, I'm just going to call those actual. So if I took my predicted minus actual, so you can see these differences, 5.6 every time. And if I actual minus predicted, and if I sum these, oh, that's not right. I'm not, hang on, I might not have calculated those right. Okay, I'm just gonna grab my old code here. I'm sure it's just oh, this is why. Because my actual, I put in adds, it should have been bought because this is our y, right? This is our y versus our y hat. So I'm gonna put y, and then here, I'm just gonna call this y hat, but remember this is just the y with the hat above it. Okay, so now if we have our actual and predicted, if I sum the differences, and this is because because there's rounding issues, but these are essentially 0 every time. And I could change this intercept and slope here. Let's change it to 11 and 0. So this is the purple line. So the one that doesn't fit very well at all. So we should have huge residuals for this, right? But when I sum it, it's 0 every time. So this is why we have to square them. So just like with sums of squares and variance, we're going to be doing the same thing where I square them. So if I square this one, now we can see we have a larger residual value than if I use 5.6 and 1, which was the red line. So we have 34 using the purple line and 11.2 using the red line. So do you see how the residuals, the summed and squared residuals are smaller? Does that make sense? So essentially, this is what we're trying to minimize. This is why it's called the least squares, because we're trying to minimize residuals.
Wait, sorry, Allison, can you explain that difference again?
Yes, so this is, so I'm grabbing the slopes from these different, the intercepts and slopes from these different lines. So I grabbed that I plotted here. So the red line here is if we just take the predicted values, so plugging them into the regression formula, right? Our intercept plus slope times predictor. These predicted values minus our actual values, which are what's in our data. If I just sum those differences, I always get 0. But if I square those, this is the actual residuals that we're trying to minimize, right? So, so this is the sum of the squared residuals. If I take the values from the purple line, which you can see by looking at the graph is very poorly fitting. And then I run this again. You can see my squared residuals are 34. So it's a larger value. And remember, which makes sense because it doesn't fit the data well at all. So it's the larger number reflects how poorly it's fitting the data.
Got it. Thank you.
Yeah. Oh, sorry. Just now saw the chat. You're getting error in the AV lines. Do you have the parentheses correct? In this on the LM statement, just you want to make sure that your parentheses are
Yeah. Yeah, my
around the LM and
parentheses
then around
are correct. Yeah, no, I don't. There's no issues with the parentheses. We can move on.
Is it when you run the first one? When you run the first line, or does it
it's
go on?
the. Oh, I see what I did. I was putting so the three AB lines. I was putting LM in that code.
Oh yeah. So AB line, it just draws the line. AB line takes an intercept and slope. So I
was just like
grabbing
copying, pasting.
Yeah.
Thank you for checking the chat.
So, oh, go ahead.
Yeah, I'm getting error too. Let me see what's. Yeah, it's like I ran the points thing, the points line, and it's like I ran the AB line, which was LM bot add. So I thought at that time it worked. It's not working.
Can you paste that error in that chat
Okay.
so I can see that? See what that is doing. Okay. Let's see. Okay, so did you plot have to run the plot type?
Okay, yeah. Oh,
So you have to run the plot line first. You have to run it as it all together essentially, because if you run something else, so if you just run plot axis, the plot is no longer, or if you run like intercept, for example,
yeah, no, it's okay, let me see one by one what lines are working.
perfect. So
Yeah.
so anyway, so this is
yeah, you can go ahead. Sorry.
here. Let me copy this. Oh no, you're fine. I'll copy it and put this in the chat and see if that will help. So essentially, this is just showing, this is why we do the squared residuals. We can't just minimize the residuals. They're always going to sum to 0. We have to square the residuals. And this is also why you'll often see this called minimizing least squares or method of least squares, because it's the smallest squared residual value. It's not just the residuals in of themselves. So the way that we do this algebraically to find which line does minimizes these least squares is to solve for our regression line. So we first want to find beta 1 or the slope. So we need to find the slope first because we need the slope in order to calculate the intercept. So we have to find, essentially we need to find the angle of the line first before we can know where to start the line, because it's part of the formula. So our beta 1 is going to be our covariance. So remember the covariance that we calculated before, cov xy. And then we're going to divide just by the variance of x. So remember, x is our predictor, y is our outcome. So we're no longer just looking at how these variables are related to one another, but whether or not we can use x to predict y. So we're just going to have x in the denominator here. So whenever you, whoops, oh, not x, sorry, a adds. And so you should get 1.51 with that, I believe. Yeah. All right, and now for our intercept, now we can find, because now that we have one piece of the formula, now we can do some algebra and say, okay, well, we know we need the mean of y. So we know we need the mean of how much they bought, because we know we want the line to go through the mean, right? So look at, it's the one thing that all of these other lines have in common, right? They all go through the mean. So we want it to go through the mean. So grab the mean of y, or number of cookies bought. And then I'm going to add some extra parentheses here just to make sure it does that part correctly. So 11, and then we're going to subtract the slope that we just calculated. So beta 1 times the mean of x. So we also want it to go through our mean of x at the angle that we specified up here, the slope. So this should give us, oh, I do this every time. This is why I usually just call things x and y. Okay, and so this gives us 2.8. You guys getting something similar? 2.803, I guess. So I'm actually going to capitalize this, just stay consistent. Otherwise, I'll never remember how to do this. So now let's see if we add AB line with the beta, our slope and intercept that we calculated. Okay, so our intercept is beta 0, and our slope is beta 1. So let's see if we run this plot again, if it gives us the same regression line as if we run the LM. So let's try it with LM, A bought, tilde A adds. So this is letting R do it. This is from us manually calculating it. Because it should be overlaid on that line, I'm actually going to tell it to make it a different color. So I'm going to make it green, and I'm also going to make it a different width, actually. I'm going to do this one too. I want to make this one, it should be a thicker line. And I'm going to plot this one, and it should be over it. And so now do you see how that green line is sort of inside the black line, because it's giving us the exact same line. So again, just illustrating, this is the manual way that LM is calculating the slope and the intercept. Questions about that? We could also just double check the numbers. So if I do, let's go back to how we did it for ANOVA. Let's just call this simple regression. So I'll do LM bought adds. And so you remember with the regression, the ANOVA, this is the exact same way. We're just going to do a summary statement. And this will give us all the information from this regression. So if we come up here, you can see here is our intercept and our slope. Makes sense? These are the same numbers. So this is exactly what we were doing with ANOVA, but this is actually simple regression. Except now we know, you know what intercept and slope are. So whenever you do those ANOVAs, you can, and I say, oh, you can just ignore all that information. Now you know what the intercept and the slope represent. All right, questions about that? No? Good. So now if we want to, let's do this with a data set larger than our 5 data points here. Let's, yeah, actually, let me go back into the PowerPoint first. Let me do a little bit more conceptual stuff, and then we'll come back and do it with our final data set. So that's essentially the math. It's actually quite simple math, but it's a different way to look at ANOVA or to look at error and variability you can't explain versus variability you can't explain. But remember, the whole concept of ANOVA is what is the variability due to what we have manipulated and what we can't explain divided by what is the variability we cannot explain. This is a very similar concept, right? Because we're finding the line that minimizes the stuff we can't explain, that error. And here, remember our covariance between X and Y, that's the overlap. That's the shared data that's the variance accounted for, or how much variance they share. And that's going into our formula. So if you want to interpret a simple regression, the line itself may not be exactly useful to you unless obviously on plots and everything, but the actually like writing out the line. So you'd usually write out the formula like this. So you'd say y hat equals, and then you have your intercept and slope, and then you just say parentheses x because it stands for whatever your predictor is. And so it's not really going to be that useful always to write it out like this unless you're using it to predict something. So let's say now you want to pull in new data. So let's say you had GRE scores and the graduate school GPA of a bunch of students. And so you run a regression and you use GRE scores to predict their graduate school GPA. And then you take that formula and then next year during application season, they look at the GRE scores of all the applicants and they feed them into that formula. So, right, and then they can say, well, based on our regression line from previous year students, these new students' GRE scores, we can predict that they would have whatever GPA. And that's whenever they would use that sort of, or you would use that regression line formula there. But it can tell us, so unless you're doing prediction, it's not going to tell you a whole lot other than, how to plug in the numbers. And you guys you understand whenever was making the prediction numbers to illustrate the concept, the lines concept earlier, I'm just using that formula. We were just saying intercept plus slope times our values, right? And you could put in new values and then you could predict, okay, if a student gets a GRE score of 155, you plug in that formula and then you get their predicted GPA, if that's what this was for. This was with cookies and number of ads. So this is, if we show 2 ads, how many cookies can we predict that they will buy? Does that make sense? So, but the regression equation can also tell us things about the general principles and that we have tested and modeled. So the intercept is going to tell us the predicted value of y when x is 0. So if there were no x, or if x has no value, then what is the predicted value of y? And so this intercept is actually only meaningful depending on your data and your research sort of design. So let's say that you are predicting self-esteem from weight loss, for example. The intercept is going to tell you what level of self-esteem to expect from someone who has lost 0 pounds, which that would be an interpretable thing, I guess. But if you were predicting self-esteem from actual weight, that intercept is not going to be interpretable because it's going to tell you what self-esteem do I expect from someone who weighs 0 pounds. So then all of a sudden that's not very meaningful, right? Because it's when x is 0. So you have to think about what your x value is as to whether or not you can interpret your intercept on your raw data. If you have data in which that is an issue where it actually doesn't make sense for your data to be 0, because there's plenty of data where, like, for example, reaction time is like this. So what in cognitive neuroscience, if you wanted to predict, accuracy, so you have a speed accuracy trade-off, you want to predict accuracy based on their reaction speed, your intercept is not going to be very informative for, what is the accuracy can I expect when the reaction time is 0? Well, the reaction time is never 0. That means they didn't do the task, right? They didn't react. There is no 0 reaction time. So in that case, you want to do mean centering of your data. So if you have something, if you want to be able to interpret your intercept, that is, where you subtract the mean of X from every X value that you have. So now when X equals 0, that actually means X equals the mean. And then in that case, you have to think about, if you've mean centered your data, when you interpret your intercept, you say, okay, well, my predicted value of Y is, you know, let's say my predicted accuracy with the speed accuracy trade-off, our predicted accuracy is whatever. When X is 0, that actually means at the mean of X, because you've mean centered your data. But now your intercept has meaning to it. Makes sense? So if you ever see in papers where they say they've mean centered, that's what they're doing, where they're just shifting all the data around the mean so that the value of 0 corresponds to the mean. So one word of advice with all of this, you should always be cautious with these interpretations. Whenever I'm saying, you know, with the predicted value of Y when X is 0, or how much Y, you know, what is the predicted GRE scores when, or GPA when GRE is whatever. That sounds like I'm saying, it can sound like I'm saying GRE scores cause this GPA, right? Because we're predicting based off of it, but that's not necessarily what we're saying. So because we use a lot of statistical language that implies causation, you have to be very careful with this. So sometimes it sounds like we're implying causality, but remember, if it's a correlational study or correlational design, it doesn't imply causality. So like the GRE scores GPA thing, that's not causal unless you manipulated somehow for people to get really bad GRE scores and really good GRE scores and then examine their GPA or something like that. But without that manipulation, you're just measuring GRE, you're measuring GPA, that's completely correlational. So that doesn't mean that GRE scores result in a certain grad school GPA. Right. And that's actually one of the problems with using GRE scores for grad school GPA, because it's actually not predictive of performance, despite the fact that you guys always have to do it. It's not quite predictive. Well, it's not predictive of graduate school success in of itself. Turns out there are a lot of other factors that go into
I
it.
think they removed it now, at least for CUNY.
Oh yeah, I think I did see that. I didn't know if that was still in place. I thought they did that just for the pandemic. Is that still the case? There's no GRE? Maybe.
I think universities like one at a time are all just getting rid of the GRE in general.
I mean, I'm very much in favor of that, because standardized testing is only good for people who are good at taking tests. And studies have shown that it actually doesn't. This is just one of my rants. It actually doesn't predict graduate school.
No, I love this. Is my favorite rant. Go on.
Do I?
Go on. Yeah.
I don't like it because it was like, I feel like I have trauma from taking the GRE because it was so stressful, and that was like years ago. It was like years and years ago. But it also doesn't predict graduate school success. I know plenty of students who scored very, very highly on the GRE and did not do well in grad school. And I know people who did not do well in the GRE and did very well in grad school. And studies have shown that that actually is the case, that you can't just use one score to predict grad school success per se. Okay,
And this
sorry.
is
Wait, I have a question now. So I didn't have to take the GRE to get into this program. Will I have to take it to get into the next one?
For PhD programs at CUNY.
Probably not CUNY, but like, yeah, a PhD program.
They're dropping them at a lot of places now. They keep it. That's the trend.
Yeah, a lot of, at least whenever I was applying to PhD programs in 2014, and they every single one of them required a GRE. Every single one of them.
yeah.
Even if
think,
you
like,
have
a
like
lot
a
of-
graduate degree like before it.
Yeah, I
Like
was
if you have a
coming from-
master's to show that you still have to do the GRE. That sucks. That's
Well,
so
I had to do a
stupid. I
GRE
hate
to
that.
get into my master's program. So I had to do a GRE to get into my master's program in 2012, and then I retook it because I didn't do well in the writing section. This is just ancillary information. I didn't prepare for it before going to my master's program. I was an idiot. And I was just like showed up and took the test. I was like, oh, I'm good at taking tests. Didn't know there was a writing section, just like completely did horrible. But I did really well on the other components. But in psychology, the writing section is very important. So I retook it just for the writing. Basically, I re-traumatized myself just to get my writing score back to a like normal
Yeah.
level. So
I think, yeah,
go ahead.
the writing section is very hard. It's very hard to think about something like just to get with a topic and just write a coherent essay in 30 minutes, until you practice a lot. And it was traumatizing for me too, because I would feel like just like you can get 330 if you study for a month, and I was like going over it again and again, and I was like, yeah, it's a very stressful test.
Yes, it's very stressful, but it turns out there's a structure. If you are I mean, I guess at this point in the year, you guys aren't taking the GRE, but there's a structure. If you just follow like the classic, like, and it's so stupid. No one writes like this anymore, like not in scientific writing, but if you follow the classic, like thesis statement, evidence, conclusion, recapturing your thesis statement, that's basically the key to getting a decent score on the writing, I've learned. But yes, and I had to take it a second time because I took it in the first time I took it, it was the old score style. And the second time I took it, they changed. So I had this like issue where no one was understanding my scores because there was like this transition between the 800-point scale and the 170 scale at this time. So anyway, it was a nightmare and I'm traumatized by it and I'm not supportive of it. So.
I think that like initially, like at least I think for this program, they waived the GRE because of COVID, but I think more and more programs are like just waiving it in general because they're realizing like it might be stopping a lot of people who would do well in the program from being in the program. And just that it's not the most descriptive test in general. So like, I don't know, I'm really happy I didn't have to take one. I got the book, started studying, and then the pandemic happened. So
yeah, it's horrible and it's expensive. I also think it's a little classist because it's expensive to take the GRE. Some people can't afford to take it more than once. I had a friend in grad school and she took the GRE. You could only take it once every 6 weeks. She took it every 6 weeks because her parents were paying for it. Like she just kept taking it over and over. And I was like, this feels a little unfair at a point, right? Like,
Right.
and all the books are expensive and like all the classes. And so I just have a angst.
wait, did she
about
end up doing well though? The one who took it every 6 weeks?
Eventually she got a little bit better. Like she got her scores improved.
I mean, what's she doing now?
She is a visiting professor at a university. So she's doing okay. She doesn't have her own lab or anything. So she's just like sort of like an adjunct, but a little bit more permanent. So yeah. So
Well, it sounds like she was successful, but yeah, I think education is just kind of classist in general.
She did switch PhD programs midway through her first one. So it wasn't
I mean, she made it. Good for her.
She made it. But yeah, it wasn't always a smooth ride. But yeah, so I have a problem with a lot of the grad school.
Also sending scores to schools also takes money, which is another annoying thing.
Yeah, because it's expensive and transcripts and all that. I have an issue with, in general, the classism within the academic and education system. It's definitely not for the common normal person. It's for wealthy people or people born into an educated family.
Yeah, I paid $5 for my transcripts to go here, and then they lost it, so I just spent another $5. So,
oh wow, yeah,
which isn't much, but it could be if when you add it all up.
It could be because I did not have at this point I'm just ranting, but I did not have my life together when I was young. Like I went to college and everything, but I was not really sure what I wanted to do. So then I decided I wanted to do like psychology and cognitive stuff. And so at sort of the last minute, so I was taking a bunch of courses to try to prepare myself for grad school and be able to eligible. So I had like 7 transcripts because I was taking classes from like community colleges and like a bunch of different places. And some of the transcript fees were like $25 a piece at one of them, and another one that was like $10 a piece, and it adds up. So it's like every time I applied to a school, I had at least $70 in transcript fees just from like adding up all the transcripts and stuff, which is my own fault, but you know, it's expensive.
No, but that still shouldn't be
So
a thing.
expensive. Yeah, that's still terrible.
And then you have the grad school application that's like $125 just to apply. The GRE scores, what's the GRE up to now? Like $200, $300. Then
Yeah, it was like 200 some dollars.
And don't
I
they
kept
have the thing-
rescheduling and I lost $50 every time I rescheduled. That was on me personally, but
and don't they have the thing where if you send the scores to the schools that day, you don't pay, but if you do it after, you have to
yeah,
pay.
yeah. So you
Yeah,
have
that
to
was-
know like the codes for the school you
Like,
want to
in that
send them
moment.
to.
Oh yeah, I do remember that. Or you have, but
Yeah, especially when you're freaking out about about the
Already about the
exam,
test,
you're not
right?
thinking about what.
Yeah, and then you have to like
yeah.
memorize these things to send right after you get charged.
yeah, I do remember that. Yeah, it's like $25 a piece, or at least it used to be $25 a piece per school. So, and I also had friends during my master's program who were, I did not do this, I couldn't afford to do this. They applied to 20 PhD programs. So every time you send scores, transcript, PhD applications, it's like hundreds of dollars per application, and they were applying to like 15 to 20 different schools. So it's very expensive for sure. All right. Sorry, got distracted there. Okay, so end of the rant session on my PhD, my upsetedness about grad school. So clearly, clearly it wasn't a system for me. So anyway, so if we go back to regression, so when you want to interpret your regression, just be aware that if your study is not set up for interpreting causality, so you didn't experimentally manipulate things, you cannot interpret causation, even if it sounds like you're wording it like we're predicting something from something else. That still doesn't mean it caused that. It's still just a prediction. It doesn't mean that X caused Y. You can only do that if your experimental design allowed for it. And so whenever you predict your slope, so that was predicting your intercept, now predicting your slope. So this are 1.51. Here, this is the change in predicted Y for a 1 unit change in X. So you can also think of this as your rate of change or your predicted rate of change. And so this often is quite meaningful. So let's think about an income education, how fitting, an income education model where we're trying to predict, oh, it really should be the other way around, shouldn't it? We're trying to predict income based on education. We can, if you're predicting or you're interpreting the slope, you would say, okay, how much of a difference of income would be associated with each additional year of school? So a 1 unit change in education. So each additional, if your educational variable was measured in years, for example, each additional year of school, what is the difference in income? So how much more or less, what is the change in income? Could also do this with fuel efficiency and car weight. So how much can increasing miles per gallon for every pound of weight a car is reduced? So you can, it doesn't always have to be an additive thing. It doesn't have to be each additional year of school. It can also be if we reduce the weight of the car by 1 pound or 10 pounds or whatever, how much does this increase fuel efficiency? And so these are just your raw regression coefficients, your intercept and slope. But you can also have, or your slope here, you also can have standardized regression coefficients, and that's typically when you see the capital B for beta. This means the same thing, but now it's expressed in standard deviations. So this is just a standardized measure. Standardized regression coefficients are probably not very helpful for you right now in simple regression, but once we get to multiple regression, it'll make more sense. So in multiple regression, you're going to have multiple predictors. So right now we just have 1x, but eventually you're going to have 2, 3, 4, 5 X's. And what if they're not all on the same scale? Interpreting the slopes for each of these is going to be more difficult, right? So, but if you standardize everything and talk about everything in terms of standard deviation units, then everything's on the same scale and you can actually just compare your beta values. So if you're looking at standardized beta values, you can directly compare them if you have things on different scales. If everything's on the same scale or you only have one predictor, you don't actually need this because you don't need to standardize to anything if everything's on the same scale or there's only one thing. But it just helps with interpretability and comparing across different predictors. So let's say, okay, we fit our regression line, now what? So you can fit any line to any data set, right? Because the math, you can always do that math. Math will always work, but that doesn't mean that your regression line is a good fit, right? We just know that that is the fit that minimized the residuals, the squared residuals or least squares, but we don't know if that's actually a good fit. It could still be a really bad fitting line, or the residuals could still be too high. And so the regression line is essentially only based on the data. This might not actually reflect reality. So we need some way of testing how well the model fits the observed data. And so we generally refer to this as a goodness of fit test. And so this fit is maximized through finding the line of best fit. So we find these parameter estimates. Oh, by the way, that's another term. Beta 0, beta 1, or your intercept and slope, we often call parameter estimates or beta estimates. So if you hear someone talking about parameters or parameter estimates, that's what they're referring to. And this little epsilon character here, this represents the error term that we always append on to the end of that, our line equation. And so although your error is minimized in this process, it's still not zero. So remember we talked about, you're never going to have a zero error. At that point, you've probably overfit your data and violated linearity, or you've duplicated something somewhere, because there's always error somewhere just because of sampling. And so we need to quantify and evaluate this goodness of fit measure. And so whenever we look at goodness of fit, we have this line of best fit derived from minimizing our sums of squares residuals. So remember, all we did was this predicted observed from predicted squared and sum. This is the same thing as saying sums of squares residuals. And this is a word you've seen before in ANOVA. Remember our SS residuals, what's left over that we can't explain? That's what this is. It's the same thing, because regression is ANOVA. It's just the opposite way. It's just a different way of looking at it. But we have our minimized sums of squares residuals, but now we need something to compare it to. So we have this minimal amount of sum squared residuals. Now what can we compare to see if it does a good job fitting our data? So, sorry, my dog is being loud. So if our model is any good, it should explain more variance than the simplest form of the model. So if we have, I know she is a mess. Sorry, I'll just show you guys. She does this on the bed. And just grumbles like a gremlin for no reason at all.
Are they trying
Is
to
she
tell you
having
you want to get
nightmares?
down?
Oh, they can get down. They just can barely get up.
Oh, they get down.
Oh,
Yeah, they have to be like lifted up because they're too stumpy to get down.
so
to get
you
up.
just lift them up at the beginning of each class?
Yeah, I mean, or the beginning of the day. Sometimes they lay there for like 10 hours a day. They're lazy.
Wait, so you could tell people I have to leave, pick up my dogs, and mean that.
Yeah, literally, like I have to pick them up because, yeah, it's a problem. We used to have stairs, but they didn't trust them because they weren't anchored.
How much do they weigh?
The little one, the gremlin one, is about 55 pounds. The one is about 70.
Oh my god.
She's not even 2 yet, so she's still a puppy technically. All right, so goodness of fit. So I'm getting very distracted tonight. Clearly I'm not on point here. So we have our minimize sum of the squares residuals, but we need something to compare it to. So think about all of our null hypothesis significance testing. We're always comparing to something, right? And so if we think about, okay, well, we have this model using this predictor, what is a good default thing to see if our model is predicting better than something else? So the baseline prediction, if we did not have X and you had to explain or you had to guess how much, how many toffee purchases or cookie or whatever we're saying here, someone was going to buy, and you had no X information. So you didn't have any information about how many ads they watched. You only had how many toffees they bought. And you had to and I would say I was going to randomly pull someone out, and you had to guess about what that number would be. What number would you guess? All you have is the Y data set. And you have to estimate how much toffee someone purchased. What number could you use? That would probably give you a pretty good estimate.
The average amount of ads watched.
The average, or no, you would do the average number of toffee purchased. So let's pretend you don't have ads, you only have toffee. So
Okay.
let's say we didn't collect the ad data and you just have the toffee data. And you
So
just want to say, how many toffees did people eat or purchase?
The average amount of toffees.
Exactly. You pull the average amount of toffees because that's the best information you have. And we know based on our distribution that the mean is going to capture, within one standard deviation of the mean, we capture about 68% of the data. So you would get pretty close just using the mean. So that's going to be the simplest form of a model. So the mean technically is a model. It's just a very, very simple form. So if we want to see if our predictor ads purchased is any good at predicting our model, it should do better than the simplest form. It should add something. So it should do better than just the mean. If it's not even doing better than the mean, it's not a good predictor. So our base model that we're going to use to compare our predicted model with is going to be the mean. So we're going to use a model without any predictors, just using toffee, which is essentially just using the mean of toffee, and compare the residuals to that. And so that difference between our observed and predicted by the mean is going to be our sums of squares total. So remember, that's all the variability that's in our outcome. So if we wanted to calculate all the variance that exists regardless of our groups, how we did in ANOVA, that's sums of squares total. That's what you're doing by the mean. So observed minus predicted, but remember, predicted is the mean. Same formula for sums of squares total. And remember, when we're comparing our SS residual, our SS total, and seeing if we explain any more than that, that's essentially ANOVA, right? And we calculate out to mean square, but it's doing the same thing. So our least squares model is going to be using X to predict Y. That gives us SS residuals. Our simplest model, our base model, is going to be just using the mean of Y, because that's going to be the best estimate we have without any other information. That gives you the total amount of variability in your data. So in the toffee purchases. So that gives you SS total. The difference between SS residual and SS total, do you remember? We've done this before. What is the difference between SS total and SS residual? What do we call it in ANOVA? The very simplest ANOVA.
SS model.
SS model, right? And this is how much SS model gives us how much our model was improved from just using the mean. So using the mean minus using our predictor gives us how much our predictor improved our model. And so essentially we're just comparing the base model or SS total with our residual or our model with a predictor in it. And when we compare those two, that's going to give us an F statistic, because this is just an ANOVA. It's just a different perspective on ANOVA, because you've seen this. Remember our model of sums of squares divided by our sums of squares total. That's what gives us our R squared value. That's our proportion of variability explained by our predictor. except we called it an independent variable before in ANOVA. We'd say what proportion of variability of variance are we explaining by our manipulated variable or our IV. That was the R squared. This is the same thing, except now we're just calling it a predictor. All right, so I'm going to hop into R in the last little bit. So a lot of this is just a reminder of our sources of variance. So remember this from ANOVA, this slide, our total amount of variance within the whole data set, our variance explained by a model. This is our SS model. And then our variability that's left over, that's the SS residual. This is all the exact same thing that we're doing with regression. We're just doing it by, we're doing the math differently because we're finding the line of best fit that minimizes those residuals, but the outcome is the same. It's essentially what you're also doing in ANOVA. You're just not thinking of it as a line. All right. So when we do this test, when we hop into R in just a second, that we're comparing our base model, so just a mean model with our predictor model. And whenever we're comparing this, our null hypothesis is going to be if our predictor model is actually better than our base model, then there should be an improvement, right? But if there's no relationship between the predictor and the outcome, then our sums of squares model, the improvement due to our model should be 0. There should be no improvement if our predictor is doing just as good as the mean of the outcome. But if it's doing better, we should get some improvement. So that's the null hypothesis here in comparing your base model to your model with a predictor. And then it's essentially just the same thing, a significance test. Basically, it's indirectly testing the R squared essentially. But saying, okay, I'm predicting there's no improvement, or my null is that there's no improvement. And then if it's significant, you reject that null, saying that your model did significantly improve, or you had a significant regression model. All right, so let me go back into R and we'll show you this. All right, so let's read in our album. So we have a different data set here. This is album sales. And let me just look at our, generally when you load in data, to just take a look at it and see what you're working with. So we have our, I think this is our advertising budget, maybe. I think it's in thousands of dollars. So this is really like 10,256, or yeah, something like that. $10,256, $985,000, something like that. And that, so this is how much they spent on advertisements. And then I guess this is how the sales they had. I think this is actually album sales, and then airplay time. I'm not quite sure what the attract is, but we're only going to be looking at sales right now. So if we want to create the model, we'll call this, so we're going to do it with, we'll call it advert model. Advert model, then we're going to do LM, just like we've done before. Our dependent variable, which is going to be, so we're measuring their advertisement budget, I believe. Just want to make sure I have this right. Maybe. Yeah, so it's the amount of money they spent on advertising. So does advertising predict sales is what we're looking at. So this is actually our independent variable. So we want to say, okay, sales is our dependent. And then we want to know if advertising dollars, so the amount they spend on advertising, is it predicting how much they're selling their albums? So we create our model, and then you look at your summary of your model, just like we've done in the past. So we can see here, if we come over here, we can see our intercept, our slope. We can see we have t-values associated with these. We'll talk about what these mean in just a second. And then you also notice you have your F statistic, degrees of freedom, p-value, and R squared. All of this is similar to what you've seen before in your ANOVA, whenever we used LM for ANOVA, right? But this time we're actually not even thinking about it as ANOVA. We're just going to think about it as, we're predicting sales using advertising dollars. So if we want to get so we can draw a regression line based on these parameters. If you want to get your standardized beta coefficients, so the ones in standard deviation units, you're going to load this QuantSci library. If you don't already have that installed, you want to do install.packages. There should have been like a little yellow bar up here for you to do that. And then we're going to do lm.beta is the function for this. And then we're just going to pass our model that we've already created to it. Oh, that's not what I want to do. Oh yeah, it is. So this is our, because we only have one predictor. So this gives us your standardized beta coefficient. So this is in standard deviation units. So this is saying for every 1 unit increase in sales, and since sales is in thousands of dollars, it's for every $1,000 increase in sales. No, for every 1 unit increase in advertising dollars, sales goes up by 0.57 standard deviations. So, or standard deviation units. So there's a little bit more math you have to do when you're using standardized beta coefficients. And so I have that sort of mapped out in the PowerPoint. But first I want to get to comparing this base model, and then we'll go back and talk about how to interpret that and how to write that up. So we have our summary here, and this actually already has a p-value because we only have one predictor, so it's going to automatically do that for you. The LM function already compares it to a base model, but just so you can see what it's doing behind the scenes, if you load the car library, let's create a base model. I'll call this base model, just using the mean. So now we're going to say sales, and now you're just going to tell it tilde1. So you're telling it, I'm not going to give you a predictor. I just want you to model it against 1, which is essentially telling it, I want you to use the mean. So just use this data right here. Don't use anything else. And you can see if we do a summary of this, this is also going to give us information, but it's essentially just telling us our intercept. Notice there is no slope. Why is there no slope here? For our base model. Where does the slope come from? So this comes from the predictor, right? Because remember, it's intercept plus slope times predictor, or times x. There is no x, so there's no slope because we're only using the mean. So, but we're not actually interested in the summary of the base model. What we actually want to do is an ANOVA comparing the base model to our advert model. This is what's telling us, is this model predicting significantly better than just using the mean?
What's happening there?
Yeah, I have no idea. I think someone's mic maybe was on. So if we run this, comparing our model only using the mean versus our model with our advertising predictor, what you can see is this is significant. But notice this value that it gives you. I'm going to run our summary of our advert value again. Look at our F statistic and our p-value. Notice it's exactly the same. That's value. I don't know what's happening here.
They like mute themselves.
Yeah, I'm trying to
Yeah,
see
it's
if I can.
someone's phone number. Yeah. Someone is calling in.
Oh, that's weird. That is odd.
Well,
Okay.
yeah, is somebody who's okay, yeah. I thought like somebody who's not like by mistake clicked on the link.
Can you mute them as the host? Like since
Yeah,
you're the
that's fine.
host?
Yeah, let me see if I can do that. I have no idea. what
I
is
think you
that.
can mute everyone.
Yeah.
They're not
Yeah.
even online though. They're not even on anymore. I think they keep trying to call in from a phone and then failing.
Oh, let's see if I can. I think I can just mute. Yeah, mute all. Okay, mute new. Okay, so I think I did it. So now it should mute new participants also. So if they try to come in. Okay. Let's go back. All right, so now it'll automatically mute them, hopefully. Okay, so now if we want to, sorry, I see there's someone in the chat. Okay, so now if we want to compare our base model to our model with a predictor, we do this ANOVA, but notice that this is the same F value as if we just do a summary statistic of our LM model, because this is what LM model is doing. It's comparing it to a base model. That's where this F value comes from. So even though we used it in ANOVA, in this regression sense, it's actually just comparing it to the mean. And if you think about ANOVA from a sums of squares perspective, that's also what you're doing. You're comparing to, if we're just using the mean, because that's SS total, minus the residual, what is our improvement? Is that's S model. And is SS model a big enough ratio that we can reject the null? That's exactly what ANOVA is doing. And that's actually what regression is doing as well. But now we're just looking at it from a regression line, minimizing residuals around the line perspective, but it's the exact same thing. So I only bring this up here because once we get into multiple regression next week, we start talking about how to compare multiple predictors. You're going to want to say, okay, I want to know if adding a second and third predictor significantly improves my model. And at this point, you're going to want to start comparing, okay, my advert model with one predictor compared to my advert model with two predictors. And is that second predictor significantly improving? Because you can get to a point where you're adding in predictors, but you're not accounting for any more variability, right? Because not all predictors are going to be important for all models. If we added in shoe size, that's probably not helpful, right? That probably wouldn't add a significant amount. So you can't just throw in, this is a way to sort of test, is this predictor actually meaningful to my model? And the basis of this is starting with comparing one predictor to your base model. But you guys don't actually have to do this component when you just have simple regression with one predictor, because the summary stat does it for you, because that's what it's doing behind the scenes. That's the default, is to compare it to the mean. So does that make sense? Yes. No.
Is this a situation where, like before, when you were talking about too many groups, too many things, then you have too little power? Or is it just, okay, these extra things that you're adding aren't going to tell us much more about it? So the first thing that was significant before is we still see it as significant, and these extra things that we're using to try to make our prediction even better, they just aren't adding much. And you know what I mean? Like, does it take away from the initial at all, or?
So it does, no, it does and it doesn't. So a couple of things. So yes, it is a way to say, okay, how much more are we going to add to our model, and how much more are we going to account for? And every time you add a predictor to a model, inherently it will increase your R squared. So remember, R squared is the amount of variability that your model is accounting for. So every predictor you add will always slightly increase your R squared, just because every time you add something, it's going to sort of account for extra thing. It's going to be accounting for variability. But that's why you see this up here whenever we run a summary statement. You'll notice there's an R squared here, and there's also an adjusted R squared. I haven't talked about this yet because we've not been into multiple regression, but once you get into multiple regression, this is what you start looking at, because your adjusted R squared, notice here it's almost identical because there's only one predictor, but the more predictors you add, the smaller this adjusted R squared will be relative to R squared. So it imposes a penalty for the number of predictors you have to sort of account for that. And to your other point, as far as the first thing that you've entered it, the first predictor that you put in the model, that is actually quite important because order matters in some types of regression. So it depends on how you're going to test it. So, and this is probably beyond the scope of this class, but in hierarchical regression, you enter things in a specific order, and then you test based on that order that you've entered it in. There are other kinds of regression where you can have them entered in simultaneously and be accounting for things all at the same time. There's different types of regression depending on the order. So think back to the sums of squares, type 1, type 2, type 3, when I said the order matters. That all goes back to this regression, the order that you enter in, predictor 1, predictor 2, predictor 3, that can influence your results depending on the type of regression that you're doing. So yes, and then you can test subsequently, okay, if I remove this predictor and hold the others constant. So that's where we get to that partial correlation that we're accounting for variability while holding other things constant in your model. All right, so this is sort of the general overview of simple regression. I'm going to just hop back in the PowerPoint really quickly for one last thing, and then we will, next week we'll have our last class where we cover multiple regression. I might wrap up a little bit of stuff. Sorry, I can't find my PowerPoint. Okay, I might wrap up a little bit of stuff on simple regression so we can go into a little bit more detail on simple regression. And sort of doing a little bit more exercises, because I feel like it's sort of a different way of thinking about data than we have done up until this point. But essentially, whenever you are interpreting your regressions, whenever you're looking at those intercepts and slopes, so we're not going to actually be manually calculating intercept and slope like I showed. That's just so you understand the concept. You'll be running an LM function, a summary, and then grabbing the intercept and slope. And at least for the purposes of my class, I'll be having you sort of interpret it. And so in the ALM example, the intercept was 134. And because the data is in thousands, so you multiply by 1,000 for interpretation. So when your intercept's 134, what we're really saying is 134,000 albums were sold when $0 was spent in advertising. So remember, your intercept is what is Y when X is 0. So 134 when 0 is spent in advertising. Your slope of 0.96 is going to be 96, so times 1,000. More albums are sold for every $1,000 increase in advertising. So notice everything's by 1,000 because that's just how the data is scaled. And so whenever you interpret it, which makes it make more sense, because to say 0.096 albums are sold for every $1 increase in advertising is more removed from the actual data that you're dealing with. So you sell 96 more albums for every $1,000 increase in advertising. If your slope is negative, this word becomes decrease. So the direction of your slope changes how you interpret it, right? If it was negative, then you would lose 96 albums for every, or you had 96 albums more sold for every $1,000 decrease, or you would lose 96 albums for every $1,000 increase, whatever. So you have to flip the sign of one of these if the slope is negative. The standardized beta coefficient is where it gets a little bit more complicated, and for simple regression is kind of unnecessary, but just to understand it, remember it was 0.57. So really what this is saying is as advertising increases by 1 standard deviation, so 1 standard deviation, you would just multiply out and find out what 1 standard deviation is of advertising. So here it's 485,000. Album sales increase by 0.57 standard deviations. And so album sales times your standard deviation times 0.578. So this tells you that album sales increased by 46,000. So it's a little bit more complicated when you're dealing with standardized beta coefficients if you're going to actually write out the interpretation. Most of the time when you use these standardized beta coefficients, this is going to be in multiple regression when you're wanting to directly compare which predictor is contributing more to your model, which we'll talk about next week. Because then when they're all on the same scale, you can just skim through and then say, this one, you know, beta 1 is bigger than beta 2, so beta 1 is more important, for example, or predictor 1 is more important. But for now, we'll just stick with the simple. Next week, we'll go into the multiple regression. So are there any questions? No? Everyone's good? Everyone understands regression?
No, I'm sure we all have questions, but at this
I
point,
know.
we're digesting even what you threw at
I
us so
definitely
that we
understand.
can perhaps ask you a question in an email
Yeah, definitely
with tier
understand.
marks. Yeah.
And then I'll try to get the assignment 6. So assignment 6 will be mostly regression based concepts, but it's going to be conceptual stuff. So you won't really be doing you won't be doing anything in R for regression for assignment 6. That's not to say you won't have things on the final in R for regression. So it's still important to know, but since it's more of a conceptual thing, since you've already been exposed to the code, I think it's more important to get a good grasp on the concepts of it. Mean for the midterm, I believe it was 90, 89 or 90. I didn't look at I can't remember the standard deviation. I think I did look at it, but now I can't remember. I'll have to get back to you on standard deviation. But yeah, it was very high. It was very skewed to the positive side or to the higher grades. So. All right. Any other questions? Both. Oh, yes, that was both combined. So I combined the scores and before looking at them. Although I did scroll through. I didn't actually look at the distribution of Part B, but it was still. I would say usually it was very close to your Part A score. So which I wasn't expecting. I was expecting I was expecting a lot of super high scores on Part A and maybe more low scores on Part B because you guys seemed very panicked when you submitted it. But it seemed to correlate pretty well. All right. Well, if there are no other questions, then you are free to go, and I'll see you next week. And it is our last class. So